Hi and welcome to Unit 2, Topic 2, Video 5. And in this video we're going to talk about application of trig functions. Now I'm not going to do anything super exciting, just to remind you some of the rules that you will have learnt in math methods and take you through a couple of harder problems. So you've just been through all the trig ideas and concepts. You may see applications in terms of tidal movement, moon phases, temperature fluctuations, circular motion, seasonal variation of different situations, and about a million other things. So I'm going to go through two examples. In video 5 we'll go through question 1, and in video 6 we'll go through question 2. So question 1. Given the approximate tidal heights at Mackay can be given by the function below, approximate when a ship that requires 4 metres of clearance could enter and exit the harbour. So let's just go through. 4 metres of clearance, that's meant to be pink. 4 metres of clearance can enter and exit the harbour if the first high tide occurs at 9 AM. Give your solution to the nearest minute. Okay, so this nearest minute will be important. Let's do part A. Now it does say approximate, so there's no function given. And so when it says approximate, I'm actually going to go through and approximate like this. You're probably not going to get this question in the specialist exam, unfortunately. So remember, a ship requires 4 metres of clearance. So I've got to do a little bit of interpretation. There's my mark at 4 metres, but in terms of clearance, a ship's going to float on the water. So if the water is this shallow down here, well, the ship's going to obviously be sitting on the ground. So clearance is going to mean that it needs to be above that value. So first high tide occurs at 9 AM. Give your solution to the nearest minute. So what I might do to make my life a little bit easier, I might just call this 9 AM here. And it doesn't give any information about when I'm starting. So actually I might change that. And I'll make this 9 AM because that's a high tide, so that's okay. And I'll give all the information for beyond 9 AM. And of course, I've got information here for the first 14 hours. So I'm going to give all the information for the first 14 hours, which takes us to 11 PM. So this is 11 PM. And that's the best I can do with the way the question's written. So it's approximate. I'm going to approximate that this is about a quarter of the way along that line. I might just rub this out so I can have a closer look. So this value, yeah, about a quarter of the way along the line. So we're talking about 2.25, which from 9 AM is going to be 11:15 AM is the end. And I've got this value here, which is going to be a quarter of a way towards 10. So that will be 9.25, which of course is 9.75, sorry. 6:45 PM is the start. And you'll notice it stays above that 4 metre height for the rest of the way, up to 11 PM. So I'm going to formalise this by making the claim that any time from 9 AM to 11:15 AM, or from 6:45 PM to 11 PM, the ship could enter the harbour, based on the parameters I've been given or have been implied inside the graph. Okay, on B, in question B, sorry, on a certain day, Mackay is expected to have a king tide, which will have the effect of increasing the height of the tide from the mean by approximately 20%. So the mean here, I'd say that's 5.5, and I'd say this is 0.5, and the mean is 3. So we're going to have a 20% increase on the mean, which is going to affect my amplitude. So given this, when can a ship enter on this day? I'm going to assume that in this case I have to be a little bit more accurate. So I'm going to build this model. So I'll zoom out a little bit so we can see the graph. And my model build is going to look like, in fact I'm going to come in here, I'll build it and then I'll move it. Model build will start like this. So first I've got my D value, which is my centre of equilibrium or my midline, and that's going to be equal to 3. And my A value is my amplitude, which is 2.5. I'm just reading this straight from the graph. Now I've got peak to peak is 0 to 12. So I've got a period of 12, which means that I've got a B value of 2 pi over 12 or pi on 6. And then I've also got my C value, which is 0 if I use a cos function. So if I use a sine function, remember I need to shift it to here because the sine function is on the up from the midline. And so that gives me that the height in metres is equal to 2.5 times cos pi on 6t, I'll put that in brackets just to make sure it's clear, plus 3. So let's take this working now and we'll pop it down below so that I can, oops, that's not really what I want to do, nor is that, so that I can use it. I'll select, I'll move it using my mouse. Okay, so let's just get down to here. And now I'm going to use that function. I've got my second question just hanging about there, so I'll move that. I'm going to use that function, this one here, and I'm going to let it equal 4. But first I have to consider the 20%. Now the 20% away from the mean is going to affect the amplitude. So therefore A will be equal to 1 plus 20%, which is 0.2, times by 2.5, which I can tell you is equal to 3. So we've got a new one, height number 2 model, is 3 cos pi on 6t plus 3. And of course I'm being asked to find when this is equal to 4. So I'm going to put in 4 equals 3 cos pi on 6t plus 3, which means that 1 is equal to 3 cos pi on 6t plus 3, which means of course that cos of pi on 6t is equal to 1/3, and pi on 6t is equal to cos inverse of 1/3, which, if you'll bear with me, I can calculate right now. I'm going to do that thing where I check my calculators in radians, and it is because I've got a pi in here, so we're dealing with radians at the moment. So I do my shift cos of 1/3. Keep in mind it is positive, so I'm expecting this to be a first quadrant answer, and the other answer will be a fourth quadrant answer. And so this is equal to 1.23 radians. Now, keeping in mind that at the moment, because of the graph, I know I've got an idea of what's happening. I'm going to go from 0 up to, not 12, but I'm going to take it up to 14. So I want my solutions to be t is greater than or equal to 0, less than or equal to 14. Now, I've got pi on 6t though, and I need to find all my solutions in the range first. So that is 0 is less than or equal to pi on 6t is less than or equal to 14 pi on 6. Now, obviously this hasn't come out with a nice exact value, so I might just swap that 14 pi on 6 to be 14 times pi divided by 6, so this is about 7.33038, etc. So I'm looking for that as my upper bound. So I've got my solution now. I've done my cos inverse of 1/3, and now I'm going to find my other solution by using my cast diagram. I've got little workings over here. Cast diagram. I've already got my first solution in the first quadrant, which is about here or whatever it is. My second solution is going to be there, which is going to be 2 pi minus 1.23. And then I'm going to have this solution here. I'll have another one there, 2 pi plus 1.23. And we'll see where we get to. So I'm going to do 2 times pi minus my answer. And that gives me a second solution of 5.05 C. And then I'll probably get a third solution by subtracting 2 pi from my answer, gets me back to where I was. And then I'll do 2 pi plus my answer, and I get 7.514. And that's outside the range, so I don't need to worry about that one, which is kind of good. I can now use my upper bounds, but first I need to calculate the value of t, which is equal to pi on 6, it's equal to all these things divided by pi on 6. I don't have to worry about two of them, so I get my first solution, which came from, I'm just trying to be exact here, to make sure I get it to the nearest minute as suggested. And It's that divided by pi times by 6, and I get 2.35096 other values there, which I've kept in my answer. That's 2 hours after 9, so it's 11. I subtract 2 from that, multiply by 60, and it gives me 21 minutes. So it's 11:21 AM, or, and again, I'm just being very careful about this, so bear with me, recalculating my original 1.23 in exact form, and then doing 2 pi minus that answer to get that, 5.05. Then I'm going to get that 5.05 divided by pi, multiply by 6, and I get 9.64904, etc. Now subtract the 9 from that because that's 6 o'clock, 9 hours on 9 AM is 6 PM, and I get 0.649. I multiply that now by 60 to work out the number of minutes, and that gives me 38.94, so we'll go 39. 6:39 PM, which means that it can enter where t is greater than 9 AM but less than 11:21 AM, or where t is greater than 6:39 but less than, and remember we only went to 11 PM, and that should have a little PM in there, of course. Okay, so there's me walking through that solution, where there were some little nuances in the question, a little bit of ambiguity of course, but the first one had some great implications there of how we should calculate using approximate values, although I now recognise this gives you a solution to the nearest minute, so maybe I should have solved that properly by modelling first, but I didn't. And then the second one has a little bit more indication that we need to be particular. Anyway, all the best.